So yeah, my name is Akshika Sundara. So I have a PhD in ML/computer science. I worked in smart homes before some time back. Currently, I'm working in the financial sector where we focus on building ML tools for the hedge fund space to predict financial markets and also quite a lot of usage with LLM and also ML ops techniques within my day-to-day work. So that's what I do on my day job. So I found this paper really interesting, which is, as they say, is one of those sort of groundbreaking architectures that sort of um, tend to challenge the current transform architecture, which is the architecture that's been used in most of the current LLM sort of models, as far as I know. So this model, this paper, it's very interesting. I mean, mainly how they look at it, and like because of the performance gains, even though it's tested in a very small um, sort of parameter like size, like 3 billion was the maximum they've tested. I mean, there are other papers that sort of looked at later. Um, so 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 it's interesting to see the results and like how this works. Um, so yeah, so these are the sort of the references that I've used. I'll share this after the call. So got an information form, but it's ideally for people if I had like quite a lot of people. So because I've already spoke to you guys, so I know you guys, your background, etc. That's very helpful for me to understand the audience. But I'll share this later in the chat. So I think the third link is the paper itself, so you can check that. I think I'm gonna sort of like go through the first link, which is the sort of a really good visual guide to Mamba architecture and like especially the fundamentals of it. So some of it might be too trivial for you, but I'll try to like go through it and like we can have a discussion and feel free to stop me and ask questions. And some of them it's quite new to me as well. So because just the new paper that I've read. So if you have any ideas, feel free to comment on it, etc. So that will be helpful. Um, so this is like the table of contents, like what we can discuss today. Like the main thing is like focusing on like the problem with transformers, like the core components of transformers and how transformers work very quickly, and then what are the problems of transformers. And then sort of addressing this, before addressing this, like the why state space models, like give an introduction to state space models, and like different aspects of the foundational blocks of state space models. And third part, it's been the Mamba architecture itself, which is sort of a improved version of state space models. And then we sort of go through that, like especially the scan operation and hardware algorithms that they discuss in the paper. And finally, we looked at a Mamba block as well, which is um, similar to the attention block that we can sort of replace in sort of like the transformer architecture. Um, so go to my sort of this PDF I've been reading. So this is from Martin Dost. I think he's one of the authors of the LLM, this O'Reilly book on LLM. So he's one of the co-authors. This is a really good description of. So I think this is a Substack article, if I'm not mistaken. So I just downloaded the PDF. So try to make some notes and then sort of highlight, which is interesting. Um, so the Mamba architecture said like first look at like the problem with transformers, right? Like so transformers uh, generally sees any textual input as sequence. And for example, so you have this input sequence like a string, and you'll have this sort of different tokens sort of separated, and you'll have these embeddings for them. So that's how we sort of like transformer sees this input. So to add the like major like value proposition of transformers is that it can look back at any of the early tokens. So that means like because of attention, you can sort of check like as shown in the next image. So like how each word sort of impacts rest of the other tokens. Like so in that way, you have the attention metrics calculated. So using that, you can sort of train the model, the LLM, etc. So this is really effective, but at the same time, it's really time consuming, especially when it comes to inference. Um, because you have to sort of know the entire sort of attention needs to be calculated for all uh, the sequence, and like you're like the longer the sequence is going to get, the longer it's going to take to sort of calculate the attention. So that's the main reason transforms are effective, but at the same time, that's drawback. Um, so yeah, so in this stuff, like they sort of shows like the two main components of transformers. You have encoder decoder components, and so in encode is it's like so this I think this example is like for translation. So you encode using the encoder component, and then sort of using the decoder you sort of do the translation. So that's like the general transformer sort of architecture. But um, I think you can sort of focus on the decoder as well. Like that's what I think GPT is the focus. I think so. Yeah. So if you just only focus on the decoders, that becomes the generative pre-trained transformer, the GPT that's normally that we know used in most of the LMs, etc. So, for example, you pass in a string, and then you predict sort of like next word through the decoder. Um, so, as I said earlier, so it's a blessing with training because you can parallelize this and do parallel training because how it's structured. Um, so you can do attention calculation for each token or groups of tokens uh, using GPUs. So it's very costly because of the usage of GPUs, but time-wise, it's really good because you have the algorithm itself can be parallelized. So that's the sort of the value addition of transformers. This is an example
One
of.
question.
Oh yeah,
Sorry,
sorry.
one
Go ahead.
question.
Yeah, yeah.
And it might be a pretty new question. So right now the processing is parallelized, right? So are you just is just one GPU doing it, or you kind of parallelizing it into multiple GPUs across the thing? How is it today?
Yeah, it is. So it is. So during the encoder phase, uh, you do it parallelly through GPUs. For example, I'll show you in this example. So, for example, so this is like the attention mechanism. Like you sort of try and figure out like the relationship between different tokens. Like, I mean, obviously, these have very strong um, attention because it's the same word. So if you know that, rest of it, so like the name and the word Martin, I think, so have a stronger relationship, so it has higher value. So each of these sort of like getting this relationship value doing this calculation, it's attention value calculation can be done parallelly. So this specific value and this specific value can be done parallelly. So that's why you use GPUs. So that's why we say that transform architecture has, especially the attention part, can be parallelized. So all the computations can be done parallel. You don't have to wait um, until one of the like the previous token to be like previous attention value to be calculated. So that's the good part. So does that make sense?
Yeah, it does. Thank
Awesome.
you.
Yeah. Feel free to ask questions. So it helps to sort of understand the missing bits. So yeah, I mean, the I think like for transform, there's quite a lot of like pretty detailed like um this like visualizations. I did this. I saw one from I think what I can't remember the YouTube channel. It's called 3-1 Blue or something like that. This guy does maths videos. He does a really good video on transform, how the attention works and like how the training happens. It's really good. If you got some time, check that out. That sort of explains how it's done. So as I said, like it's really good during training, but during inference, it's gonna sort of trouble us a lot. So that's because um, so you have to sort of recalculate the attention for the entire sequence. So that means like, for example, after you generate like the sixth, like you have this L length sequence generated, but to generate the next token, you have to calculate attention for all of these again. So that means you have to like do this matrix calculation again. So I mean, you can parallelize individual components, but still that means you have to calculate it again. So generally it's L squared computations. So that's the problem. So whenever, if the output sequence is long, so you'll have to like recalculate sort of the each tokens sort of, again, like each, let's say, words relationship with rest of the words, and see like how do you sort of generate the next word. So that's why it's sort of like problematic during the inference stage. So that's why I say it occurs with inference transformers. So yeah, so this is like the summary of it. Like simply like it's fast during training, and during inference it scales quadratically with sequence length. So it's going to be really painful if the whatever you're generating is too long. Yeah. So I think like you guys are quite familiar with RNNs. So they have like quite opposite transformers. So what like recurrent neural networks basically, this is like you get two inputs, one like the input itself, and the other one is like the hidden state of the previous time step, t-1. So I'll show you like a diagram what it does. So RNN, so you have the input, and you have a hidden state, like so you use the input and the hidden state of the uh, previous stage, and use that to get the output. So this is like there are multiple sort of layers to that, and this is like how it will be unfolded. Like you first do this, and then you do this. So this hidden state get updated. Uh, and so you use that hidden state to sort of maintain a relationship about the previous tokens, like what sort of meaning in that sentence is that. So that sort of hidden state will keep that meaning. So you can use that to like sort of progress with sort of to train the model, progress with the training of the model. So that's what RNNs does. So this is, as we looked at transformers earlier, this is really good when it comes to inference phase. But this is going to be really painful during the training phase. So this is a much more clear example. So you sort of pass this. It's the word hello. My name is. So this specific. But if you pass in this, so you can see like you sort of learn the word hello. So this added to the hidden state, and then you predict the next word, and then the next word is that the exclamation mark, and that's been added to the hidden state. Likewise, the previous one's added into the hidden state. But it's important to highlight that, like, for example, if you go here, it's sort of losing the first one, like the red color one. It just, I mean, it doesn't always happen, but it depending on the size of the hidden state, like how do you store this, like how you compress this information. But just to show that there's the concept called, I think the name of it's called gradient. Can't remember. It's basically like you're losing certain information as you train RNNs, because like the tokens that were like at the early stage of the sequence, whether it's words or any kind of input sequence, tend to get lost. So you might lose certain important information during this kind of training. So that's trying to show you. Yeah, RNNs tend to forget information over time since they only consider one previous state. I mean, it only considers the previous state to train, and it might have some of this information, but it might forget some of that as well. Yeah, other thing is training cannot be done parallelly since it needs to go through each step at a time sequentially. So you have to finish this step and use that internal state to pass it into the next stage. So likewise, you can't like the vanilla RNN, like RNN as it is, original RNNs, you can't like sort of do it parallelly. So yeah, this is another sort of showing like inference scales linearly with sequence. Then so yeah, so you can sort of add like sequence length can be infinite, to be honest. Like so you can like generate any. I mean, still there's a limit, but like it's not gonna get like so the time is linearly scale. So it's really good, not like transformers where it get really slow if the context like the output that is generating is too much. But during training, it's gonna take a bit of time because you can't do parallelization, even though with transformers that you can do that. So it's a bit of a pros and cons situation. Transformers are faster with training, but inference is slow. For RNNs, it's the other way around. I mean, slow because you can't parallelize that. So to address this, so these researchers try to come up with Mamba, but like Mamba itself is like a improved version of state space model, which is concept from statistics. So in this section, the author of this blog post has written really well, like what state space models are, like what are the sort of the fundamental building blocks of state space models. Does that make sense up to now? Sorry.
Yeah.
Awesome. Yeah. So
where did Mamba? I mean, is there a particular like? Did it come from any? I would say organization. Like
yeah. So I think
a team.
yeah,
Yes.
yeah. So there's it's from a university like research team. So I think I'm not sure. Maybe University of Michigan. So they've written the paper called Mamba. I'll put that in the chat after this. It's funny that the initial sort of paper got rejected from I think ICLR or something like that. So it's like one of the top ML conference. It got rejected like probably last year. But yeah, so there's open conversation. Like you can see like the rebuttals that like the reviewer comments, like why they are sort of like not accepting this paper. There's a really interesting article, not article, but like open review. I think that's where they've had it. So if you Google Mamba open review, you'll see like the authors and the reviewers are discussing this, like why it was rejected. But this seems to be like a really promising pathway, what you can like do, building new sort of LLM models. So yeah. So yeah, it's important to understand what is a state space. So generally, state space is basically you sort of represent a system with its possible states. So I'll show an example in a bit. So you try to like represent like mathematically represent sort of any kind of a system using the current state and the next possible states, etc. So you have this mathematical simulation, so you can do certain mathematical computations on that. So that's what state space sort of means. So it's called state space representation. So this is one example. This is just imagine this is like sort of a map, like a grid. This is I think like you have XY coordinates. So you are here. This is your current state. It's represented as your X coordinate and Y coordinate. You can go to next stage. So this is another sort of representation, like where you can go to next. And this is like general state. Like, I mean, this is not relevant to this, but this is like another way of like another location in this map that also can be represented as XY coordinates. So this is like trying to build up like how to come up with state space models. So this is like a state space, I guess. So these are called like state vectors. So state vectors. So it's basically like different states as vectors. So you have XY coordinates. So this shows like in this. So this is like using XY coordinates. So the three sort of locations we saw, you can have like these XY values, and the second right hand one is basically distance to exit. So if you go back, so that's exit, like what's the distance to exit? So you can sort of see the distance to exit. Like there are different pathways that you can go from each location. So that also can be represented as a vector. So on the y-axis, distance to vector, distance to exit, and on the y-axis, you have the actual y value on the map itself. So you can represent like different locations like this. So that's what generally state space means. So yeah, it's another important point is like state of a system is typically it's a hidden state. So that means you can't. So that means like a latent variable, like you can't directly observe that, but it's a value that you can derive from other observable sort of data points, and but that is really crucial for us to understand the system and like to figure out how the system would behave. So that's my understanding of states and a hidden state, what it means. So yeah, that's another important sort of a terminology that we need to understand. So what is a state space model? So like the original concept, so it will have like three components. So you have sort of an input sequence. So for example, move left, down in the maze. So it's also sort of represented as xt. Then the latent states representation, that's like the value I mentioned that it's like a hidden state. So that's like distance to exit and xy coordinates. These are not directly observable, but like actual important information of the system of that state. Then then derive predicted output sequence. So what would be the next sort of next step? So you'll have this. So YT can be calculated from these values. Okay, let's see what is. So yeah. So generally, state space models, the original concept, they've used continuous sequences, like not discrete values. So that's what the theory says. Like you have like a x sort of continuous function, and if you do this transformation within state space sort of model, you'll get output sequence, which would be like sort of like predicted sequence. So we'll go more into what's in this black box. So yeah, it's here. So you have like generally two equations within this model. So you have state equation and output equation. So state equation sort of um, represents like the next hidden state, like h dash t, and you calculate that by the A, B, C, and D are matrices. You multiply A with current hidden state ht, and you like add that to B is another matrix times xt, that the input sequence. That's how you calculate the next state value. Then to get the output, that's like the y. You need to do this calculation. So you do matrix C multiplied by current um, hidden state plus dxt. So d is another matrix, and xt is the input value, and then you get the yt. So that's how we sort of like to predict the next state and the output. Does that make sense? Sorry, first time I read this, it didn't make sense to me. So just want to make sure that you understood that. Sorry. Sorry, just want to check if that makes sense.
Yeah.
Oh,
Sorry.
awesome. Yeah, yeah.
Sorry,
So,
my mic was mute. Sorry.
okay. No worries, no worries. I
Yeah.
just want to check. Yeah, cool. Um, so yeah, so the so so generally state space models, like its goal is to find like state representation such that we can go from input to output sequence. So this is what like the black box means. Um, so yeah, uh, so these two equations are the called state space model. So I think this is the fundamental sort of two equations. Um, so yeah,
Um, Hi.
yeah,
Uh,
yeah, good, yeah, go ahead.
so just to like clarify, so will it be appropriate to say like the model architecture is essentially just like it's kind of a three-step thing where uh, one is like kind of a state selection and then you state update and then there is like an output where essentially like in a state selection stage where you kind of update the states based on like relevance of information and then kind of you updates the selected states while keeping the rest unchanged. I don't know if I'm trying to compare it with, I don't know, in like an LSTM you kind of have some sort of a memory thingy which
Yeah,
allows
yeah.
what.
That's correct. So you basically you try to like sort of with the input, you see like how the input and the previous state sort of impacts the next state of the system, and
Yeah.
you sort of calculate that, and then use that and the input itself to calculate the next state. So that's basically how we sort of so just yeah,
Okay,
that's
I got
correct.
it. Got it.
Yeah,
It's like, so essentially it's like in LSTM LSTM chooses what to forget and what to remember.
exactly,
Okay.
exactly. Yeah,
Got it.
yeah. So you can sort of, especially the matrix A,
Mm.
you can sort of even be like you can structure the metrics in a way that sort of like what sort of sections to focus on, what sort of sections to forget. And I think like there are certain like there's metrics like I think called hippo. I think I don't know if it's algorithm or metrics type. So use that to like sort of filter out specific part of the state or the input itself. So like you have like across the diagram, like the top part of the matrix is all zero, so you sort of like drop off certain parts of the input. So in that way you focus on very specific part of the input sequence or the state. So yeah, you are correct there.
Yeah. No, it makes sense then because maybe because of this type of linear time complexity, that's what makes it very useful on long sequences. I mean, seems.
Yeah, yeah,
Yeah. Okay. Clear.
that's true. Yeah.
Yeah.
Awesome. State equations. Yeah, so yeah, this is like sort of reiterating what I mentioned. So state equation, this one describes how the state changes through matrix A, that's AHT, based on how the input, based on how input influences the stage through matrix P. So these input and the current state, how that impacts the next stage, and then you'll have so yeah, so this is like a bit more like visualized representation of that. So you have matrix A, you have the HT, which is the current state, and plus you have B, which is another matrix, and the input. So you do like a dot multiplication, um, um, and then use that to get the next sort of updated state. Um, so HT refers to all latent states representation at any given time t, and XT refers to at some input. So the output equation describes how the state is translated to output through matrix C and how the input influences the output through matrix D. So if you look at this, it's very similar. So you have the matrix C, and you have the state, the current state, and then you also have the input itself, and then another matrix, and with the summation of these two results, you get the output. So that's how we get the sort of next prediction. So all this now sort of can be sort of summarized like this. So you have x coming in, it's multiplied by d, and it's added here, and So that's for to get the y value, and then from a input state point of view, you have x multiplied by b. It's going to h, and you have the previous h multiplied by a, and is added here, and that sort of impacts h, and then h means the latent space, the hidden state, and that's sort of contributing multiplied by c, and then added here, and then you get y. So that's how sort of the calculation is done. And I think there's a reference given in this document, like this is the calculations are done. Like you can go there and like annotated paper on this. So it's good to check that out as well. Okay, let's see what this part. Yeah, so it's basically sort of explaining a bit more. So you first get multiplied by matrix B, which describes how the input influences the system. So yeah, it's B times 60, like how the input itself changing the system, and then so yeah, it's sort of expansion of this one actually, this specific step. Sort of building the same thing. So you multiply B with input, and you get this one, and then you multiply sort of current state with A, and you get this new hidden state. So sorry, this value, and you sort of add them together, you get the next sort of hidden state. Yeah, so you, as I said earlier, you sort of get the state representation value, like the hidden state, and then sort of multiply that with C, and you get value here, like C times HT, and then you also get D times XT, which is coming from the top, and then you get the output result. So yeah, I mean, just note here, like this is considered like a skip connection, so which is I think this is very common in computation, it seems. So you sort of, if you want to sort of pass in the input directly, maybe after certain minor adjustment, but not going through the entire pipeline, you do a skip connection. So you pass in through like this, and then that is sort of aggregated at the end to directly sort of influence the output itself. So yeah, just don't want to lose information from the input a lot. So they do that. So it's called skip connection. Yeah, so you have the state space model here, and then you have a skip connection, and that's the sort of the general state space model altogether. Yeah, think let me see if that. Yeah, so I think it's the same equation. They sort of like remove this skip connection, which is the input value, like to show it separately. I think this being the state space model, the focus being, yeah. Yeah, I think so. This is the next part. So if you guys have any questions on this section, feel free to ask. So this is like another step that you need to do.
Yeah, so no, I mean, I don't have a question on topic, but I'm wondering, like, because I can only see the state equation and output equation. Are you scrolling the page, or were you, or am I
Oh,
not
sorry.
seeing?
Oh, sorry. Okay, maybe I'm not scrolling.
Yeah, just wanted to check.
Let me reshare, maybe. Let me see. Sorry. Can you see now? Sorry. Or is it still the same?
Oh yeah, now it makes sense. Yeah, I think
Okay.
because you were talking, I think, and the page was still stuck on the.
Okay.
Yeah.
All right. Sorry. Yeah. So yeah, this is like the next part is like from continuous to discrete signal. So what it means, I mean, very simple thing. Like you, so you have to. So if I'm not mistaken, generally, if you have a continuous signal, So maybe this final states representation is analytically challenging if you have centers. So you let's see. So we generally get like discrete input like text, etc. So you have to convert that to continuous signal. I think so. That's what it does. Let me see, from continuous to discrete signal. I thought it's the other way around. I mean, let's read through it. Let's see. So this the technique that they use called zero order technique. What it does is like if you have an input discrete signal, you convert that to continuous signal by sort of holding the value until a new value sort of comes up. So if you have like value, let's say this is I don't know, there's no value, but let's say 3. So it's just hold it at 3. So it's until from time 0 to 1, it's 3, and then you do a step to the next value, and you hold that value, etc. So you sort of hold it until the next value sort of arrives. In that way, you can convert like a discrete to continuous signal. So just want to maybe check why it is done, but yeah, that's something need to check. So the amount of time that you sort of hold this value, it's called step size. So it is another parameter that we control within the okay. Now that we have continuous signal for our input, we can generate a continuous output. Only sample the values according to the time step of the input. Okay, so yeah, I mean, if you have continuous signal, so you can sort of run this run it through the model and sort of get a continuous signal out, and then you can discretize it based on the same parameters that we use, like using step size, etc. That is my understanding. So probably need to play around with the code a bit to see like how is this sort of playing around. Yeah. So yeah, this is like sort of the mathematical description on how you apply zero order hold. So to discretize, to get discretized matrix A, you write it like this, and to get discretized matrix B, you do this. So this is step size. Okay, not sure what it could be exponential. I believe so, but I could be wrong. So I mean, the other things are generally the same. So identity matrix, inverse function. So you have this, do this calculation, and you can sort of discretize it. So you can like do that sort of transformation. Yeah. So basically, what it does is like if you get a discrete signal, you sort of do the conversion, and then get a sort of a pseudo continuous signal and use that to run it through the SSM, and then you can sort of reverse the results to get the discrete values as the input that we got. So I think that's my understanding of this piece. So that is needed to run this on this model. We use K instead of T to represent discretized timestamps, and to make it a bit more clear. Yeah, so I mean, yeah, instead of T, they will use K. That sort of represents the timestamp, or like the step size that's been used, because that can vary rather than the normal timing that could have different kind of step as well. Yeah. Okay. Then you got the recurrent representation. Let me show you. So yeah, it's sort of like referring back to what we looked at RNNs before. So how we can sort of use the RNNs approach within the SSM, how that can be sort of applied here. So I mean, it's what we discussed earlier. So then this sort of ties back to that. So you at timestamp 0, I mean, this is the same thing here. At timestamp 0, you get h0. That's the hidden state, which is b dash x0, but there's no previous hidden state in the initial sort of input, so that part becomes, this part becomes 0. So you directly, it's b dash x0, and then when you get y0, it's c h0, which is the previous state, like h0 c into h0. So you get this value. So then you sort of like move to the next stage. So you get the state of previous timestamp here, and then you get b dash x1, and you calculate the next hidden state and use that to calculate this y1. So likewise, you sort of continue. So you sort of train the model with each and every token that you get. So that's how we sort of train the model in the RNN sort of fashion. So that's how we sort of look at how RNN sort of can be used when sort of using state-space models to be trained to train using sequences. So yeah, so this is like a side-by-side comparison how RNN would look like. So I mean this is folded, so that means like there are like multiple layers behind this, similar to SSMs. You have multiple layers here. So the recurrent the recurrent side of SSMs. So yeah, they have sort of expanded that as well. So what it means is like you'll have the A dash sort of matrix here, and you have the hidden state. Use the input times B, A times hidden state, and then you multiply it by C, then you get the Y. So likewise, then this hidden state get updated, and then you use the next input, this hidden state, to get the next Y value. So likewise, you just sort of go ahead, sort of doing a recurrent training. It's important to highlight that these values in this state, A, C, B, are constants. I think they don't change at the moment. So yeah, this becomes a problem later on. So we'll sort of address that at the actual Mamba architecture, how this is addressed. So yeah, it's fast inference but slow training because it's sequential. Then you got the convolution representation. So SSMs would have both RNN and CNN sort of embedded in the different parts. So yeah, so I'm sure you guys are quite familiar with kernels, where you use like filters, like yeah, this one example. So in CNN, you sort of have a kernel. So you have this large image, and you take different pixels and you run it through a kernel, and you get to, let's say, average value. Sort of if you reduce the sort of compress the results into like a smaller pixel, or even like do a filtration, you do this. I mean, correct me if I'm wrong. Like I'm sure you guys know better than me on this topic. So similarly, like we look at this from a one-dimensional point of view. So you have a kernel, and you have the input sequence, and you do this transformation. That becomes sort of like the next word prediction. So that's the output. So you sort of play around with this kernel so that this the results can be sort of transformed, like filtered to get the right next word. Yeah, so this is what they're saying. So yeah, so this is the kernel. So this is like set of the long sets of like matrices like that you can sort of multiply it with. So you have the input value. So different parts of the input will be multiplied by different parts of the like these multiplications of the different matrices. So you use that to sort of get the output. So there's a worked out example here, much more detailed. So if this is the kernel, like CA-2, B dash, CA dash, like yeah, these are all matrix multiplication, which results in matrices itself. So this is a very common thing in like convolution. You have like this padding added, like especially if you're starting off, especially at the edges, like if you don't have the at extreme edges, you tend to add padding so that you try to capture everything all the elements at the edge. So this is like you add like 0 0 here, and then sort of they don't get multiplied, but it just to get the calculation going on correctly as well. And then you got why not here. So you then sort of move this window across for each token, and then so yeah, this is the second token. So you move it by one, and then you get the y1 value. So for y1 value you get CAB x naught, this one, plus CB x1, this one. So you get like my name is, so you get the output here. So likewise, you can do this transformation across, and you get this sort of y2 like this. So the issue with like sort of CNN in this case is like the fixed kernel size. So the inference is not as fast and unbounded as RNNs. So these are like two ways that you can do like SSM calculation. So that's what they're saying, and both have pros and cons. So yeah, and then so they sort of summarizes these three representations. Like you got the continuous time, so that's the original one, and then you after discretize these values, you get the recurrent one or the convolutional one. So you recurrent one efficient in inference, but parallelizable training is not possible. But convolutional, you can do parallelizable training. This is why computation can like projects can like do like use GPUs a lot, and then unbounded context. So it is not unbounded because it's dependent on the kernel size. So you can't like have infinite sort of context, and so that's what they're saying, I think. Yeah, so what they're trying is here is like you use one aspect of like during training we use the convolutional representation, which can be parallelized, and during inference we use efficient recurrent representation. So you try to get like best of both worlds in this case. So in training mode you use convolutional. So so you have this fixed size kernel, and then you sort of run it through the entire data set, and then sort of, but because you can use parallelizable sort of training, it's very helpful, and you can do it very fast. But in inference you use convolutional side of things, and then you use so the context length, you can have unbounded context length in theory, I think. So they call this linear state space layer. I think this model is supposed to have a linear state space layer where they have convolution at training, and inference they do recurrent. So yeah, I mean, to better understand, we have to actually implement it and then see. And they have implementation on GitHub. You can sort of run it with your own data if needed. Yeah, namely that linear time. Right. So this becomes a problem. This means that matrices A, B, and C are the same for every token the system generates. So that means like linear time. So these values are like the matrix A, B, C wouldn't change depending on the token. So that sort of becomes a problem. So that's what they're sort of highlighting here. And yeah, so in other words, regardless of what sequence you give the system, the values of A, B, and C remain the same. So we have a static representation, which is not content aware. It's quite opposite to transformers, where you have that tension. It's very context aware, content aware. So yeah, so then yeah, they before going to Mamba, they sort of like I mean, we covered most of the Mamba right now. Like Mamba is just add-on to this one, and then they sort of go into matrix A, like why it's important. So yeah, matrix A, it's basically captures information about the previous state to build the new state. So what you do is like it's basically like a matrix that sort of can maps the internal state, so that like multiplying by matrix A sort of tells you what would happen to the internal state depending on the input. That's what matrix A means. Yeah, and since matrix A produces the hidden state, so that's what it does. Creating matrix A can therefore be the difference between remembering only a few previous tokens and capturing every token we have seen this file. I mean, I think this is what you mentioned earlier. So where the A controls like what sort of elements to focus on and what sort of elements to drop. So that's quite important. So yeah, they use this high order polynomial projection operators, hungry, hippo, or hippo. So hippo attempts to compress all input signals it has seen thus far into a vector of coefficients. So this is like how it's done. So you have the input signal, and so reconstructed signal. So you convert that into like vector of coefficients. So you can do mathematical operations on that, but at the same time, it sort of so for all the steps, there's a so you tend to forget all the sort of tokens, if I'm not mistaken, and then like for the closer ones, it's much more focused on those tokens. This is my understanding. So it uses matrix A to build a state representation that captures recent tokens well and decay older tokens. Yeah, that's what it's saying. So yeah, so this is the formula for that, and it's much more easier to understand looking at the visualization. So if it is like a n by k, like 4x4 matrix, so values above the diagonal become 0, and yeah, the diagonal becomes n plus 1, 1, 2, 3, 4, and this is the everything below the diagonal. This calculation 2n plus 1 to the power of like 0.5. Is it a multiplication? Not sure. We'll have to actually input values and see. But this is the matrix. This is one of the metrics that could like the style of metrics that A can be. So yeah, building matrix A using Hippo was shown to be much better than initializing it as a random matrix. As a result, more accurately construct newer signals. I've also noticed we've gone beyond time. So I mean, I can like quickly move all this and like show like rest of it. Like, what do you guys think? Like, 'cause I know like don't want to take a lot of time from you guys. So I can like, what do you guys think?
I mean, yeah, I mean, you can skim through it, if time is
Yeah.
about. But I'm sure. I think this is interesting. I'll definitely read the paper. And
Awesome. Yeah. Cool. Yeah, I think like we are almost sort of like at the sort of the part where I sort of like go into the details. So yeah. So yeah, they sort of explains like so the idea behind hypometrics is that it produces hidden state that memorizes this history. So this Legendre polynomial, I'm not sure, I'm butchering this name. So it's basically I've seen this like during my undergraduate days. It's basically I think like use like split sort of signal like smaller signals, something like that. So you can sort of do calculations because of that transformation. But I could be wrong here. But that's how it's done. Um, yeah. So Hippo was then applied to the recurrent and convolution representation that saw before to handle long range dependencies. So it basically like because of this multiplication, like sort of calculation can handle long range dependencies. Yeah, so it's called like structured state space sequence. Like S4. This is still not Mamba yet. So, but these are like the 4 components like that SSMs have, like state space models in general, and you have Hippo for handling long range dependencies, and you discretization for creating recurrent and convolution representation. So that's what it has. Yeah. So, but I think it's important to highlight like some of the problems. We can't finally have came to like Mamba. So selective SSM. So we finally have covered all the fundamentals to understand Mamba special. So state-based models can be used to model textual rich sequence, but still have sort of disadvantages we want to prevent. So I think let me see. Yeah. So I think I think this example shows like what problem does it attempt to solve. So like this sort of goes to synthetic tasks that they looked at in the paper. This is really well shown. Um, it's called selective copying and induction heads. They try to solve this using SSMs, like the structured state space model, the previous version, not the Mamba version, and show that it doesn't work. So this is called selective copying task. What it does is like you have these cats love playing with yarn. So you have this like sequence, and you want to do like a selective copying, but it wants to the task is that you have to maintain the sequence order. So you want to copy cats and yarn, but you want to make sure that this order is maintained, etc. So SSM performs well in this task since it's linear time invariant. Yeah, so because the metrics A, B, C are constant, every token, it's same for every token that the system generates. So that it becomes a problem. So you can't it can't properly solve like selective copying, like picking up cats and yarn. And then as a result, an SSM cannot perform content-aware reasoning since it treats each token equally as a result of the fixed ABC matrices. So this is one problem. And the other one is like the SSM performs poorly on its induction heads, where the goal is to reproduce patterns found in the input. So this is one example. This is like I think chain of thought prompting. You give an example, like question is like this, answer is 2, and you give another prompt, what is 2 plus 2, and supposed to give like 4, but it is unable to, regardless, so it's unable to perform this properly regardless of what the input x is. Matrix B remains exactly the same, and it's therefore independent of x. So it sort of shows like because matrix B stay the same, whatever the input you provide, sort of the calculation becomes the same. So because of that, it can't pick what from the example that's given what sort of tokens to focus on. So these are some of the problems that SSMs have. So yes, these tasks are relatively easy for transformers since they dynamically change the attention based on the input sequence. So to fix this, Mamba gives selective scan algorithm and a hardware aware algorithm. So the selective scan algorithm, which allows the model to filter irrelevant information, and hardware algorithm, what it does is like generally they look at the calculation, the algorithm, to they change how the calculations are done at different parts of the GPU rather than sort of doing back and forth IO operations with the SRAM and the DRAM of the GPU, where DRAM is it's less efficient but has bigger space, where SRAM is high efficient but has smaller space. They tend to like do most of the calculation in SRAM, so because of that, they can do these calculations much faster. So that's one example. So selective scan. Let's see. I think they've done a selective retain information. So they basically build something in between like a transformer and RNN. So you have this something state size, which is not large as like transformers attention sort of metrics. You have something in the middle that sort of stores enough information. So that's one aspect they have tried. And then, so this is the calculation of that. But I wouldn't go much detail into that. But it is basically you try to like selectively picking information and how it's done. That's how they are sort of shown. And the other step is a scan operation, which is so the whole RNN business that we looked at, because RNN sort of do the training sequentially. So you use the previous state to the next one. So because of that, you can't do parallelize that. So what they've done, like a really good trick here, I think it's really interesting to see. So they've sort of expanded the RNN sort of calculation and mathematically looked at like what sort of previous latent states input like is impacting the future state. That's my understanding. And you sort of construct future states with the derivative of a previous state. So likewise, you have a future states that can be like part of a future state can be calculated by calculating, like for example, like in previous state. So that's my understanding. I could be wrong here, but because I haven't done the maths in this example. So because of that, they can do like future calculations as well, and then do the computation parallelly rather than sequentially, like to a certain extent. So yeah, it's O n divided by T. And this is the hardware algorithm I mentioned. So you have generally do this DRAM, SRAM sort of calculation, like you do copy in between DRAM and SRAM. What they've done is to get everything to SRAM, do the calculations, everything here, and then move it to DRAM. So in that way, it's much more faster. I don't know how scalable this is, but for the testing they have done, so it looks quite promising. So done the most of the calculation the fast run. Yeah, so this is how they say they're like, it's called kernel fusion. So yeah, it's basically like you sort of do the calculation piece together. Yeah, I think this is recomputation. It's the same. So this is another aspect of the algorithm, that, like hardware algorithm. So what they mention here is like so intermediate states generally like not saved. So what they've done is like doing the propagation, backward pass. These intermediate states are recalculated. Like so, even though it sort of looks like it is not efficient, inefficient, it like they have proven that it's better to like do this recomputation rather than like sort of saving doing more IO operations to save this information in the DRAM. So maybe that's correct. So I think that's what they've done. So even the intermediate state they have like recalculated during the backward pass. So with all these stuff, they have sort of created this one. This is like the selective SSM, which is the Mamba architecture. So they have this in green and orange. So the orange, that's where you have the calculation in the SRAM, and then the other ones like it's the DRAM in the GPU where you have this information. So and you get the input, and it is sort of goes through a projection, and it goes to multiplied by matrix B, matrix sort of delta, like step size, and then matrix C. So you do this selection mechanism here, and then you get the multiplication. And as we discussed earlier, it's basically like sort of multiplied by matrix A, and then you do this over and over again for the rest of the input sequences to build a model. So this is a really interesting paper. And also there are like so just the final note here, like this specific Mamba sort of architecture like can be as a Mamba block. That's what they call, like it's similar to attention block, so you can sort of plug that in within like normal transform architecture. You can replace the attention block with Mamba block, so that so you can sort of have a number of Mamba blocks within this architecture. So I wouldn't go into this because I think like this is yeah, I mean, it would take a bit of time to like, sort of explore this. But yeah, this is how they've come here. Like you have the transformers, RNNs, where you have Mamba. I think this is really important to sort of look at least for 3 billion parameters. Transformers, like they Mamba is fast in training because parallelizability, and inference is also faster because scales linearly with sequence length and unbounded context. So in the paper they show like how it sort of compares with 3 billion parameter size transform model, vanilla transform model, and like how it's performing really well. So yeah, so this is like the Mamba sort of architecture, like mainly the fundamentals of it, and like I think this should give you guys enough background to like go and read the original paper, and I'll share this link in the chat. So yeah, happy to take any questions.